Hey everybody, this is Professor Ross, and in this video we'll be talking about the correlation coefficient. Let's take a look at some notes. Our key learning objective as we talk about the correlation coefficient and the rest of our content in this unit is about using the logic of statistical decision making. So we're trying to understand how to make decisions and using the correlation coefficient as a useful tool there. So in this unit, we have a new variable type of pairing. We have examined in this course a single proportion, a single mean, pairs of variables like a categorical explanatory and a categorical response, both binary, and a categorical explanatory and a quantitative response. In this new unit, chapter 10, we're going to explore a quantitative explanatory and a quantitative response. And so both our variables are going to be quantitative variables. And the step one, when the research question and the study design and data, step two, are focused on two quantitative variables, then exploring the data can be done graphically with scatter plots. So this is our third step of our 6 steps. And we want to explore the data. And one of the key tools for us when we have two quantitative variables is to use a scatter plot. I've got an example of a scatter plot here. It's too small to see on the screen. The next screen we'll get a little closer look at it. But basically we have our explanatory variable on our x-axis, so one quantitative variable along this axis, and our response on the y-axis, the other quantitative variable here. And a dot represents a value both on the explanatory value and on the response value. So each dot represents an individual. We're going to examine 4 things when we take a look at a scatter plot and try to explore our data. So, and these are numbered, and the order is important to do the number 1 first. After that, the rest can kind of fall in any order. But the first thing we have to determine when we look at a scatter plot is what do we feel the form of the data is. And for our purposes, the main decision we want to make is, does this look like a linear form or a more complicated curve or other nonlinear kind of arrangement of the data? What do we mean by a linear form? Well, basically, if you can take most of the dots, the bulk of the dots, and draw some kind of straight line through them that seems to be a reasonable trend in what you see in the data. So I like to think about this as if I can draw a straight line and make an oval around it and capture most of the data in my oval, that's usually a pretty good sign that we do have a linear form for our data. Statisticians tend to be eager to say that we have a linear form because we can often do a lot more. And little strays from the linear form, things outside here, or even if this oval has to be fairly wide to capture it, they're still fine with calling that a linear form. We start getting into nonlinear forms when we see data that very clearly follows some kind of curving pattern, and then we say, oh yeah, a straight line doesn't capture that data well, we need some kind of curve. So if the data is just kind of scattered about, we're often okay with saying, yeah, we could put some kind of line through there. It might not be a strong relationship, but linear is okay. After we've decided the form, then we can talk about the next 3, strength, and that's how close the points follow the form. So if I were to draw a line through here, how close or how far are my points from that form? The closer they are to the form, the stronger. So here, my points kind of spread out a little bit. Here, if I drew this curved form, the points would fall almost on it. This would be a super strong kind of form. Or excuse me, yeah, super strong relationship, but not linear, of course. The direction, and we can only speak of direction when we have a linear form. So that's another important reason why we want to talk about linear first. And the direction is positive when higher values in the explanatory go with higher values in the response. In other words, as you go from left to right on the scatter plot, if you're going uphill, that's a positive direction. Negative is the opposite. When higher values of the explanatory go with lower values of the response, that would be a downhill kind of direction. And notice that if you have something like a curve, it can actually, change direction. So we typically don't speak about direction when we have a curve in our data. Lastly, unusual observations, data points not near the form. So once again, we need to know what our form is first, and then decide, oh, we've got somebody that is not near the form. That's an unusual observation, sometimes called an outlier. So form, strength, direction, and unusual observations. Here's a little closer look at that graph on the left is the one from the previous slide, and another graph on the right. I encourage you to pause the video at this point and talk through for yourself and maybe jot down what do you think the form, strength, direction, and unusual observations are for each. I'll talk through those and we'll go one at a time. With form, we'll take a look at both of these. Both of these statisticians would be happy to call linear form. So we can draw a line that's a reasonable uh, model or trend of what's happening in the data. So you may have looked at those and thought they don't really look like lines. So that's one thing that students commonly kind of feel initially. But once again, if you can draw a line and put an oval around it and capture a lot of your data, um, typically we're feeling like that's a pretty good linear form. So both look linear. How about strength? So strength is about how close the dots are, and these have somewhat similar strengths. This guy here might have a little bit less spread around it, besides maybe an outlier or two. This one, the oval has to be a little bit wider. So the left one might be slightly stronger. But one thing about strength is it's somewhat hard to judge visually. And so that's part of what we're going to get into in this video. We're going to talk about a measure of strength called the correlation coefficient. Next, direction. We have opposite directions. This one over here is a positive direction, and this one here is a negative direction. One's going uphill from left to right. The one on the right is going downhill from left to right. Lastly, unusual observations. And you might have noticed when I drew my oval around here, there's at least one unusual observation on this one. This guy here is also a kind of borderline, maybe an unusual observation, maybe not. Over here, similarly, we probably have a borderline, one or two, where these guys here might be borderline unusual observations. And those are often the most interesting for us. So like in the context here, this is ACTs and how they relate to GPA. And this person here has a very high ACT, but not as high of a GPA as we would expect. And that's part of why it's an unusual observation. We might expect somebody with that high of a ACT to be up here closer to the 4.0 GPA. This one here, the relationship might seem a little stranger, how tall you are and how much it costs to go to Maryville College per year. I just surveyed students about this. And here we had an especially high cost for someone who was fairly short, or here a higher cost for someone who's fairly tall. There's a very strange trend here. And one reason why we talk about correlation does not mean causation. It looks like taller students are paying less to go to Maryville College. We don't necessarily think it's their height that's causing that to happen. Okay, so that's looking at scatter plots and getting a sense of what's going on in your data. Really valuable to explore your data and find out what seem to be the trends and what's going on. As I mentioned, strength can be a little hard to judge, and so we have a statistic that can help us with that called the correlation coefficient. It's a numerical summary for the association between two quantitative variables when they have a linear form. I'm going to highlight this for us. The correlation coefficient does not give us any meaningful information if our data does not have a linear form. So if we have some curved data or other kinds of nonlinear things going on in our data, a correlation coefficient is not the appropriate measure to take. And in fact, it can be misleading. So it's really important to explore your data with a scatter plot, look at it and say, hey, that does look like a linear form, then we can calculate the correlation coefficient. We symbolize it for a sample of data with the letter R. And so R means correlation, and R ranges from -1 to 1. So it's a decimal value. It's greater than -1, but less than 1. R measures both strength and direction. when R is, direction's the easy one. When R is positive, the direction is positive. So if I have those dots going uphill like this, that means that that correlation is going to be a positive number. If I have a negative direction, if my scatter plot is indicating more of a downhill, then that's going to be a negative number for R. So that's pretty straightforward. The strength is also not very hard to understand. When R is closer to 0, the strength is weaker. So if my dots are scattered more all around, all over the place, that's going to give me a correlation closer to 0. In contrast, if I have dots that are very, very close to a straight line, that's going to be closer to +1. Or if it's close to a straight line going downhill, that's going to be really close to -1. So numbers like 0.8, 0.9, those are really strong correlations indicating my data is very closely related. My two variables are very closely related, and I've got a very clear trend going on. Correlations that are more like 0.0, 0.1, 0.2, those indicate a lot less connection between the variables and a lot more scatter going on in the data. I'm going to encourage you to pause the video and try to guess the correlation coefficient for each of these. So we'll take a look at these in a second, but one thing is that a lot of times students feel like this is a weaker correlation than maybe you'd expect. Similar with this, they might feel like, wow, that's really scattered about. But actually, these are relatively moderately strong correlations. So 0.7 is getting close to that 1.0. We're on the strong side of a correlation for the relationship between ACT and GPA, a relatively strong relationship there. Similarly for height and cost per year, but now on the negative side, negative 0.589, almost negative 0.6, it's kind of in that moderate to moderately strong negative correlation. So those are a couple of examples, but I'm going to strongly encourage you to try out some more of this because it can be really valuable to be able to look at a scatter plot and get a sense of what kind of strength of correlation we might have. And our authors have created the correlation guessing game applet amongst the other applets. So if you click on that, if you go to the applet collection, you'll see the correlation guessing game, and you can try that out there. Here's how it works. You hit new sample, it'll put a bunch of dots there, and you put your correlation guess in there. Before you guess any, I'm encourage you to track performance, and this will keep track of how your guesses do and how close you are. So in here, I've got clearly a negative trend, and boy, those dots are almost in a straight line. So I'm going to guess something like negative 0.9. Let's call it 93. And there we go, negative 0.927. So I've had a little bit of practice guessing correlations, done this a lot. So what do you do once you've tried one? Hit new sample, it'll bring up another one, make your guess, and check your guess, and it'll keep track and it'll give you a little track on how you're doing and how close your guesses are. I encourage you to try this, do maybe 10, 15, 20 guesses to start getting a feel for what kinds of correlation numbers go with what kind of visuals. All right, let's hop back to our notes here. One last thing in this video, it's important for you to know that correlations are very influenced by outliers. They're very sensitive to outliers and can change a lot. So another reason why we got to look at our scatter plots and get a sense of what's going on in our data, if we see that we have outliers, we should know that, hey, that correlation may not be worth much of anything as far as trying to interpret it. So let's take a quick look at how influential these outliers are. This was Facebook friends, number of Facebook friends that some students reported, and how many texts per day they sent. And I had 2 students who reported sending 1,000 texts per day. Seems like a lot to me, but that's what they said. So I put that data in there, I calculated the correlation. Even though this doesn't necessarily look very linear, I've got these 2 massive outliers. I went ahead and calculated the correlation knowing it would be fairly meaningless. Here it is. If I didn't look at my data, I would think, hey, there's some kind of moderate relationship between Facebook friends and how many texts per day you send. On the other hand, if we remove those 2, so those 2 outliers are gone now from our data set, Now we calculate the correlation and we see very close to zero. In fact, slightly negative, the opposite trend of what we saw earlier. So almost no relationship between how many Facebook friends you have and how many texts you send each day. This is the much more accurate interpretation of what's going on. Here, the outliers have had a bad influence on that correlation, making it less useful. All right, correlation, one of our valuable tools for understanding the relationship between two quantitative variables.